All right, we are going to be going over chapter 8. Chapter 8 is over quantum mechanical model of our atom. So the first thing we want to investigate is we want to look at light as an electromagnetic radiation. Okay, so what is light? Light is an electromagnetic radiation. It's a form of energy that has electric field component and magnetic field component. So I guess this is a magnetic field right here, and that's electric field component, and then they travel in one direction. So that's so far how we look at it. Light is kind of like a wave, right? So light can be energy, light can be seen as a wave. So we want to talk a little bit about waves first. Okay, so when you talk about waves, we want to see, so here's one full wave, here's another full, well, half of a wave because it goes up there. All right, now the amplitude is how high, how tall the wave is from the middle, okay? So it's from bottom here all the way to the top. That's how big the amplitude will be. It's how high it is. Now, the more intense the light, the brighter the light is, right? If you have a really bright light, the amplitude is going to be bigger, okay? Wavelength here is from one peak to another peak, okay? So it's basically how long each wavelength is. It's from one peak to another peak, or one complete loop here. That's the wavelength of one wave, okay? So that's measured in some form of distance. We're usually going to be measuring these values at nanometers, okay? For visible light calculations anyway. And then we want to talk about frequency. So frequency is how many waves can pass through in 1 second, usually, okay? So the unit is going to be in hertz or per second. It's the same thing. 1 hertz is 1 per second. Now, the energy for the amplitude and the frequency, so the way we say it, the bigger the amplitude, the more force it has, and the more frequently the waves strike, the more total force there is. So the total energy is going to be proportional to how big the amplitude is and how many times it passes through in 1 second. So let's take a look at a picture of frequency here. So the frequency here says, so if this is the time in 1 second, this wave passes through so many times. So like 1, 2, 3, 4. So you can see like it passes a few times there. That's in 1 second. So because it passes 4 times, we say it's 4 cycles per second, or 4 hertz, okay? Or 4s to the power of -1. And this one here, the wavelength is shorter, so it passes a lot more times than up here when the wavelength is bigger. So when you see the wavelength get smaller, the frequency gets higher. So frequency and wavelengths are going to be in opposite patterns here, okay? The smaller your wavelength, the shorter your wavelength, the higher the frequency will be, okay? And the higher the frequency, the stronger, the more energy there is for that particular wave, okay? Of course, if it's a bigger amplitude, it's stronger. All right, so the relationship between waves for the wavelength and the frequency, they're opposite. And what are they related to? They're related to the speed of light here, which is c. We'll be giving you the value of c on the periodic table, so don't worry about that. C is going to be 3.00 times 10 to the power 8 meters per second, okay? And then this is frequency here in per seconds or hertz, same thing. And then wavelength here is going to be written in units of meter, and you'll see a lot of times the wavelengths that we are going to be calculating and reporting in, it's going to be in the range of nanometers. Okay, so let's go ahead and I guess I'll show you the picture here, and then we can calculate the wavelengths based on this formula right here. But I wanted to show you the electromagnetic spectrum. So I want you guys to memorize this. Well, not the all of it, but the pattern going from radio wave, microwave, infrared, visible light right there, UV, X-ray, and gamma ray. Okay, so let's explore this electromagnetic spectrum. So this is all light energy. Okay, it's our electromagnetic spectrum, all the forms that we want to cover in our class here. The highest energy is going to be in gamma ray. And if you notice, something that's high energy is associated with something that's high frequency. The frequency is really, really high. Okay, that means a lot of them pass through in 1 second. That means the wavelength is super, super, super small. Okay, so wavelength and frequency are going to be opposite. High energy, high frequency, low wavelength. Okay, and then on the other side here we have radio waves. Radio waves is really lower frequency because it's low energy. And then because the frequency is low, the wavelength is really, really big. Okay, so now we have what we can see. The visible range here is so small in the big spectrum here. But this is what we see, so they blew it up a little bit. Now, when you're around 450 is blue. So your edge here is 400 nanometers wavelength. So I remember purple or violet here is the highest energy on the visible light and has the shortest wavelength and highest frequency. Okay, so around 400 is purple, 450 will give you blue. I guess around 550-ish will give you green. Once you hit 700, then you start seeing red. So this is like the color spectrum here. Okay, red is low energy, low frequency, and the wavelength is going to be bigger. See, 750 is bigger than 400. Okay, so you want to know the color ranges, the trends between the wavelength and the frequency and the energy. And then also you want to know radio wave, microwave. So radio wave, you see the wavelength here is so big, like it's 10 to the power 3, 10 to the power of 1, 10 to the power minus 1. So cell waves here are going to be slightly smaller. But over here, can you imagine 10 to the power 3 meters? That's like 1,000 meters. That's 1 kilometer. Like you can run that distance to fill one wavelength. So the radio waves are really, really big, okay? So just imagine how big they are. And then you go to cell waves, they're smaller. Microwaves are even smaller. So because the wavelengths are getting smaller, the energy is getting a little higher, but it's still weak because it's weak in comparison. And then we have infrared. Infrared is slightly stronger than microwave. And then we have visible light that's slightly stronger than infrared. Now, so to remember infrared and ultraviolet, red is next to infrared, violet is next to ultraviolet, okay? So UV rays are the ones that, you know, if you stay out in the sun too much, you can get skin damage, sunburn. And then X-ray is higher energy and gamma ray is even higher. So gamma ray is the one people hear about, Incredible Hulk, right? So anyway, that Incredible Hulk, that's fiction. This is real, okay? So that's our electromagnetic magnetic spectrum here. So I'll show you some pictures here. So infrared is, you know, for us to use using thermal imaging, like, you know, you can see stuff because of thermal, because of things that are hot and cold, they emit certain kind of infrared lights, and you can see, like you see the nose on the dog is blue, so it's always colder. That's kind of cool. And then you can see here for radiation, high energy radiation, we usually use like high energy, so maybe like some form of X-ray or some high energy stuff, and you can, if you can concentrate and target it, you can use it to kill cancer cells, okay? All right, let's work on some calculation on wavelength and frequency. So let me go ahead and write it out for you. So let's zoom out a little bit. So it says calculate the wavelength in nanometer. Okay. Calculate this is lambda. Lambda will be our wavelength here, okay? So a lot of times I just say wavelength, but I write this symbol in nanometers of red light emitted by a barcode scanner that has a frequency of 4.62 times 10 to the power 14 per second. Okay, so frequency here is going to be mu. That's the sign for it. All right, and our formula is frequency equals to speed of light over wavelength. Okay, so let me write it out. Frequency, and our unit is per seconds. Wavelength, units of meter. And of course, you know we reported the wavelength of red light is about, what was it? Let me show you the picture. Like around 700-ish, but look at the unit here, nanometer. The reason why we use nanometer is because the visible light it falls in the range of nanometers. And what's nano? Nano is 10 to the minus 9. So it's a really, really, really small measurement, okay? So when we calculate this, hopefully we get close to 700 nanometers, but you know, 600 something, 700, hopefully that gets close to the red range. Now, if it wasn't red, then maybe it was a different color. Maybe it was orange color. But they still say red. So, all right, so we have this here, and then we have speed of light. So that one is speed of light. Speed of light will be provided on your periodic table, and it is 3.00 times 10 to the power 8 meters per second. Okay? Okay. So let's go ahead and put this in. So what's my frequency? Let's put that in. 4.62 times 10 to the power 14 per second. Okay. And then we have speed of light 3.00 times 10 to the power 8 meters per second divided by the wavelength. We're looking for that. Okay, and now this is going to give me an answer in terms of meters. So the wavelength here is going to be 3.00 10 to the power 8 divided by 4.62 10 to the power 14. Make sure you know how to do this in your calculator. Now, when you put this in your calculator, you're going to get 6.49 times 10 to the power, we'll keep 10 to the power minus 7 meters. Okay, now we have to convert it in nanometers because they wanted you to report in nanometers. So then you go, how do I convert this meter to nanometer? So you take the fact that you know that 1 meter has, well, I guess we'll say 1 nanometer. 1 nanometer is 1.0 times 10 to the minus 9. Okay, because nano is 10 to the minus 9, right? I guess it's not 1.0, it's technically 1 because it's a definition. I'll go ahead and change it to that. Because it has unlimited sig figs here. 1 times 10 to the power 9, okay? Then we will keep 3 sig figs here. We get 649 nanometer. Okay, so that's how you would do the calculation on that. Now, the next question I have for you has to do with the electromagnetic spectrum here. So it says here, arrange visible light, X-ray, and microwave. Okay, and then they say number 1, in order of increasing wavelength, and then the second one, in order of increasing frequency, and then C, in order of increasing energy. Okay, now how will we do this? So let's take a look at the picture again if you don't remember. So you do have to have this memorized here so you know the energy levels. But since we don't know it, you just showed you, I'm going to show you this picture again. You look on your slides and make sure you have this memorized. So we have visible light, right? We have X-ray and microwave. So microwave, visible light, X-ray. So X-ray is the highest energy, visible light in the middle, and microwave on the lowest energy. Now, of course, this question can be varied. They can change it to radio waves, infrared, X-ray, ultraviolet, gamma ray. They can change whatever they want. Okay, so just make sure you know the scale here. And they could also ask you in colors if you're talking just visible light. So anyway, increasing energy is going to be from the lowest energy is microwave, going up to visible light, and then X-ray is the highest energy. Okay, now remember, energy and frequency is the same exact pattern. Okay, energy and frequency, same pattern. So I'm going to write down frequency. This is wavelength. Okay, so frequency and energy, same trend. So microwave, visible light, X-ray. Okay, what about wavelength? Wavelength is the opposite of frequency, right? Because you see how wavelength and frequency are opposites here. So wavelength will be the opposite. That means X-ray is the smallest. And then you go up to visible light. And then the longest wavelength we have in this case is microwave. Okay, what if we do the same problem? Instead of just giving you these different energies here, let's look at visible colors, okay? Visible light colors. So arrange green, red, and blue. Okay, so red and blue are on opposite sides, remember, and then green is in the middle. So red is low energy, blue is high energy, green is in the middle. So red is, so I'm going to go ahead and do C, B, and A, same thing. And then increasing energy would be the red going up to green, going up to blue. Okay? And then we say energy and frequency is the same pattern. So red going up to green, going up to blue. Okay? Now what about wavelength? It's going to be the opposite. Okay? Increasing wavelength. So for this chapter here, yes, they can ask you to calculate, but a lot of times they just ask you to go ahead and compare them too. Okay, so blue will be the shortest wavelength, and then green in the middle, and then red is the longest wavelength. Okay, so that's how you do this kind of problem here. Now, let's keep going on our slides here. So far we've been talking about light as an energy, and we want to look at it as basically as a wave, right? So we've been looking at it as if it was a wave. So hold on a second. My computer is popping up with stuff left and right today. Don't bother me. Okay, so we were talking about light energy as waves. Now we want to explore the particle energy, particle nature of light energy. Okay, so we're saying we observe something called the photoelectric effect. So I guess I should show you what the photoelectric effect picture looks like. Basically, if you shine a light, particular light, it depends on the energy. So energy is high enough for the light that you shine on the metal. The metal actually can shoot out electrons or different kind of emissions of light. Okay, so I'll show you the picture here, I guess. Right here. Okay, so you put in some light, shine it on the metal, and then depending on what metal and depending on what light is, you emit some stuff. So you can, if it's high enough energy, you can actually force an electron out. okay? If not, you force some other energy forms out. But they say basically you can eject electrons depending on how strong the incoming light is, whatever the frequency of it or the amplitude of it. Okay, and then the stronger the intensity, the higher the amplitude, the more electrons are going to be popped out. The frequency of the electron tells you what the type of energy it is, and it tells you what type of electron will be ejected out. Okay, now remember, sometimes depending on experiments and what you do a lot, sometimes you can put X-rays in and you can take electrons out. Sometimes you put X-rays in, you can get like colors coming out, maybe UV light, maybe sometimes X-rays coming out too. Of course, it's just all different kinds of stuff. But basically, you can view light as particles, like individual pieces that you can count. Okay, so they say we knew it was like a wave, but now we can also view it as a particle. Okay, so let's go back to this picture here. So because it's particle, we are going to be looking at, so Einstein said that light energy can be counted as photons, okay? And quantized means you can count it. And so electromagnetic radiation is a stream of particles. Instead of just looking at like a wave, now it's like a bunch of particles coming out. And the energy of a photon is related to its frequency. Kind of like what we just talked about on the picture before this. The energy is high, frequency is high. Okay, same idea here. So, and then it's opposite of the wavelength. Wavelength is going to be, if frequency is high, wavelength is going to be short. So they tie this together here in an equation called, so earlier it was frequency is speed of light over wavelength. Now we just add Planck's constant in. Planck's constant times frequency equals to energy, or Planck's constant times speed of light over wavelength will give you energy. Okay, so now we want to start calculating energy of a particular photon. If we know the wavelength, we can calculate it. If we know the frequency, we can calculate it. We want to calculate the energy of particular photons here. Okay, so let's go ahead and give you a question here. There will be different forms of question, but here's one of them. Okay, so this is when you will be practicing different questions on dynamic study modules and homework questions. And then, of course, when we work on problems in class as well. So here's one of them. A nitrogen gas laser pulse with wavelength of 337 nanometer. So my question is, can you see this one? What color is it? You cannot see it. Okay, you can't see this one because remember, once it goes past 400, it's invisible to us. We can't see anymore. That's our limitation. Our eyes literally can see only from 400 to like 750. Anything below that or higher than that, we cannot see it. Okay, so 337 is going to be higher energy than a visible light. And then we want to go ahead and we won't be able to see it, but we're going to do some calculations on it. It says this is the wavelength. And each pulse, one pulse of that laser contains 3.83 millijoules. You gotta remember what milli stands for. Milli is 10 to the minus 3. 1 times 10 to the minus 3, okay? Millijoules of energy. Because it's just one pulse, so it's less than 1 joule is millijoule here. And it says in that pulse, how many photons are there in one pulse? Okay, so a lot of times, some questions will literally give you the wavelength, and they'll just ask you what's the energy of this photon at this wavelength. This question went a step further. They're like, you know what, if I have a pulse and each pulse is this much energy, you can tell me how many photons are there. Okay, so you have to find out the energy of one photon, and then take the energy of one pulse divided by the one photon, and then you can count how many photons are there. Or maybe they can tell you, well, one pulse has like good whatever number, X number of photons. Can you go ahead and calculate the energy of one pulse? So they'll give you different pieces that are missing, but you want to solve it. So I'll show you how to do this version, okay? So energy equals to H nu and then Hc over lambda. Remember, so this is frequency, that's Planck constant, that's Planck's constant, speed of light, and wavelength. So we want to go ahead and plug it all in. Now remember, this our Planck's constant I'll give you as 6, this will be on your periodic table as well. 6.626 times 10 to the minus 34 joule seconds, okay? So we call this Planck's constant. All right, so we have Planck's constant here, and we want to go ahead and calculate all that value, put all those values in there. So E equals to, so we have the wavelength, so we're going to go ahead and use that. So it's 6.626 times 10 to the power of negative 34 joule second. And then times speed of light 3.00 times 10 to the power 8 meters per second. So notice how this is in meter and the seconds cancel out here, right? So the next thing you want to cancel out is meters on the bottom. So when you report the wavelength on the bottom here, you cannot put 337 down. It is not the correct number to use, okay? So we have to take 337 nanometers and change it to meters first. So let's go ahead and do that on the side here, okay? So 337 nanometers. 1 nanometer is 1 times 10 to the minus 9 meter. Okay, so that means it's 3.37 times 10 to the minus 7 meters. And that goes here on the bottom of that equation right there. So then let's go ahead and calculate the energy of that one photon. Okay, so this is energy of one photon. It turns out energy of the photon is going to be 5.8985 times 10 to the minus 19 joules. Okay, I'm just going to underline the third one because I'm limited by 3 sig figs here. So we have that energy of photon is 5.8985 times 10 to the minus 19 joules. And then each pulse, energy of each pulse is given in our question is 3.83 millijoules, right? So I'm going to go ahead and turn this milli into joules. So this milli is 10 to the minus 3 joules, okay? That's millijoules. And if you take the pulse energy over the photon energy, it should give you the number of photons, okay? So number of photons equals to E pulse over E photon, 1 photon. So it is 3.83 times 10 to the minus 3 joules divided by 5.8985 times 10 to the minus 19 joules. So that should give you a whole lot of photons, right? How many photons do we have? If you keep 3 sig figs, it's 6.49 times 10 to the power 15 photons. So make sure you guys practice this, okay? Make sure you know how to use your calculator. I assume by now we're in chapter 8. You should be good with that kind of stuff. And always make sure to remember to use your parentheses. Okay, so while we're at this here, let's keep going. We just did the calculation here. I showed you the photoelectric effect, right? So another thing we want to do is if you have gas atoms. So we were talking about like, what was it? Photoelectric effect was shooting energy, light energy on pieces of metal. Well, if you take atoms of gas atoms, you like put energy to it, like, you know, when you excite it using electricity, or maybe you burn it up or whatever it is, just, you know, planes have colors, right? So anyways, we have atoms here that we're going to go ahead and excite it using, in this case, in this picture down here, hooking it up to electric here. You will see that whatever the atom is, whatever kind of gas it is, it gives you a particular color, okay? Whatever color. So these are all different kinds of atoms here, and then they give you color. Now, whatever the color that's being emitted here, you take it through a slit and a prism, you can see it separates it into a spectrum right here. So you record that color, and that's the color for hydrogen. So I want to show you the different spectrums for different atoms, okay? So I guess if we zoom in a little bit, you'll see this on your slide number 17 also. So this one here, you can't see, that's hydrogen right there. And then I think that's helium, and that's something else. And then that's a different, that's uranium right here. And this is going to be the sunlight. See all the colors on there? So that's the spectrum here. Okay, so this line spectrum here, like how in the world did this come about? I thought it was just a color, but turns out the colors have all different discrete lines here. Right, you see how the simplest atom has only a few lines. The more complicated atoms will have more lines here. And then the more, this one here, like uranium, is super complicated, because lots of lines in there. And then you get the sun, it's like almost continuous band. So over here, we're saying that the way we want to explain this is by using Niels Bohr's explanation, okay? So he's saying that the colors that you're seeing are due to energy levels of the atom, where the electrons are jumping around. So I want to show you the picture. This picture looks like this. Okay, so he's saying that there's a nucleus in the middle, and there's different energy levels of the electrons. So he's saying like they're orbits and they're stationary. So that's where he's not completely correct, but this is a good starting place for a model. Okay, so he does say electrons travel in a fixed distance. Now, you do probably learn this when you're in, like, I guess elementary and middle school. They tell you these things are stationary states, they're orbits, right? This is the old model. It's not quite completely correct, but we're gonna use this as a base, and we'll show you what the real model that we have right now is. So the energy is proportional to how far the distance of the orbit from the nucleus. So the further they are, the bigger the gap of the energy is here. Okay, so they're saying if you see on hydrogen, if you see a red line, that red line is low energy. So it's from a gap that's like pretty close together, like maybe from line 3 to line 2. So it's like a short jump. When the energy when this electron drops from line 3 to 2, you emit a color. So we got to talk about why when it drops a level, it emits color. But this is what he's saying. Like if you see green color, maybe it's from level 4 to 2. If you see purple color, maybe it's from level 5 to 2. You never know. Okay. So why is this so? So when they're saying right here is when you have lines here, go ahead and focus. Hello, focus. There we go. All right. When you have multiple lines here, when you shoot energy into your atom, okay, an electron on the lower level can get excited if it absorbs that energy. If you get just the right amount of energy. So it has to be the correct amount. If it doesn't match exactly to that level, it's not going to jump it. So like, you know, whatever the gap is, it's going to jump that by whatever light is. So I want to go ahead and draw it out for you in a little bit. So electrons can get excited when they absorb some energy and photons. And then when they release the photons, it relaxes and it emits that color that we saw, the red color, the green color, and the purple color. Okay, so this is the idea here. And they talk about the difference between the final initial states. So it must be the correct amount of energy, blah, blah, blah. So let's go ahead and just draw it out. Right, I'll show you a picture of it first. So level 1 to level 3, that's going up here. So when you're going up, energy is being absorbed. So this electron, if it started from level 1 and jumped up to level 3, electron has been excited here. And the only way the electron can be excited is if you shoot it with an energy that fits exactly this size gap. If it's not the right size gap, it's not going to happen, okay? If it fits size 1 to 2, then it'll shoot from level 1 to level 2. So whatever it is, in this case, it's shot from level 1 to 3. That's excited. So the electron is ground state on the bottom. Up here, it will be excited. They'll usually mark it with a star sign. Excited electron and the star sign. And then they're like, you know what stays up there is not stable. It has to come back down because it's not natural to stay up in high energy level. So what it wants to do is go ahead and relax it down to a lower energy. Now, when the electron relaxes back down, it releases energy outwards. This energy outwards here is going to be, depending on what wavelength or energy it is, or frequency, you may be able to see it in color. Sometimes you won't be able to see in color. It depends on if it falls in the visible light range. Okay, so specifically, if you were looking on a hydrogen, you see how hydrogen is like more interesting, it's more complicated. So level 1 is on the bottom, level 2 is up high, 3, 4, 5. Now what I want you to notice is from level 1 to 2 is a big gap, level 2 to 3 is a smaller gap, 3 to 4 is a smaller gap, 4 to 5 is even smaller, 5 to 6 is even smaller. It just keeps getting smaller and smaller and smaller the higher levels you go. Eventually, if you reach infinity, the band is no longer separate, it's continuous. So that's the difference between quantum, where it's separate, and classical physics, where it's a continuous band. Okay, so you can see colors here. If it's red light, you can see it from level 3 to 2, green light will be 4 to 2, purple light can be from 5 to 2. But if you have other smaller levels, then it could be infrared, you can't see. If it's higher energy, you probably can't see because it's in the UV range. So that's the idea right there. Now, let's go ahead and draw it out together, and I'll ask you some questions based on this, okay? Let's use a visual feature. So we are going to draw it out. So you can practice drawing. Okay. So let's take a look at 2 different ones. We'll talk about absorption and emission. And then we got level 1 on the bottom. I'll draw level 1. And then we'll do level 2. And then level 3. And then level 4. And then level 5. And then level 6, you start to see the idea, it starts getting closer and closer, and the higher the level, it gets closer and closer together, okay? So I'm gonna go ahead and label them. This is level 1, N is 1, N is 2, N is 3, N is 4, N is 5, N is 6. Label the same thing on the other side. So this fact here is true. The higher the energy level is, okay, the closer the gaps are going to be together. And eventually, if you approach infinity, the band will be continuous. The lines are going to be continuous band. Okay, so here's the idea here. When a photon is absorbed, okay, so when a photon is absorbed, electron goes up in energy level. We call this absorption. Okay, so an example will be, here's my electron on my ground state on the bottom there, and you're like, here we come, incoming, shoot it with a photon. So photon shoot in, and you're like, oh, that's exciting. I gain a lot of energy. Now I'm going to jump up. Whoa, it's going to jump up here. And now it's going to jump up to level 3. It's like super excited. So this is the process of absorption. Shoot a photon in, whatever gap it matches, it will shoot an electron from here to here. If your electron was in line N2, and you had just enough energy to shoot it to line 4 or 5 or 6 or maybe line 3, whatever it is, depending on the photon, it will shoot those guys up too. So the absorption is basically whatever size the photon is, the energy is, it will shoot it up, whatever the gap energy will be. Okay, so that's absorption. Now, when something is high energy, like say something maybe like got shot up to level 6, okay, it really can be in level 3 and then come back down to 2 or 1, but I want to do level 6 and we can jump it down. Level 6 electron, somebody jumped up another photons from maybe level 2 all the way to 6, and then you're like, oh, I'm up here, it's not stable. So it's like, well, let me go ahead and fall back down. Maybe it'll fall down to level 2 here. So it's going to fall down from level 6 to level 2, and in that process there, it's going to emit a photon. Whatever the photon is, if it's a certain range in the visible color, you'll be able to see the color. If it's not, then it's whatever energy. If it's high enough energy gap, maybe it's in the X-ray form. That probably has to be like a higher level emission, okay? So this is called emission. So when photon is released, electron goes down in energy level. So we call this emission. Okay, and the Niels Bohr thing was telling you that you see these colors here, these colors are from the emission spectrum. They're emitting that color. So he's saying like, oh, look, you saw red, it was because it's from this level to this level emission. Oh, you saw blue-green, it's from level 4 to 2. You saw purple, it's from level 5 to 2. That's what he was saying, okay? So that's the emission, but for it to emit, you kind of have to have it absorb something first. That's why you have to shoot it with some color, okay? You shoot it with some energy, and then light comes out, depending on what color emission it is. All right, so now that we're at that, I wanted to ask you some questions, okay? So I probably didn't need to do such a big line there. We didn't need such a big divider. All right, so my question is, which transition is an emission of the lowest frequency? Okay, so I'm going to give you a bunch of options. A, B, C, D, E, F. Because I'm going to ask you some questions, other questions based on this A, B, C, D, E, F. Okay, so I have this one, N1 going to N3. And then I have N2 going to N3. And then I have N3 going to N1. And I have N3 going to N2. I have N4 going to N3. And I have N3 going to N4. So there's all kinds of different moving of electrons here. Now remember, going up is absorption, coming down is emission. So they're saying emission of the lowest frequency. Lowest frequency would be the lowest energy. Okay, so let me zoom out a little bit so you can see the map on the top. Zoom out a little more. Whoa, sorry. Okay, so I'll just have to do this. So basically, the lowest frequency will be the smallest gap that you can find, and it's coming down in energy. Okay, the higher the number, the smaller the gap. So you want to look for something that's coming down, and it's the smallest gap. Okay, so obviously out of coming down, you have 3 to 1, 4 to 3, and 3 to 2. The smallest gap will be 4 to 3, because there's 3 to 2 and 4 to 3, but you see here, 4 to 3 is smaller than 3 to 2. Okay, so my answer here for the lowest frequency emission is going to be E. Now here's another question. Which transition is absorption of the shortest wavelength. The shortest wavelength is going to be the opposite of frequency, right? Frequency and wavelength are opposite. So the shortest wavelength will give you the highest frequency. The highest frequency means highest energy, and you want to absorb it, and it has to be highest energy. So you want to go up in the biggest gap you can find. So the way I see going up is I see 1 to 3 is going up, 2 to 3 is going up, and I see 3 to 4 is also going up. So going up, but I want the biggest gap. The biggest gap would be A. Okay? And then the next question, so you can see here, I can ask so many different questions. I can change the frequency to highest frequency or longest wavelength, or I can also ask you now, this one here, which transition is the absorbance or absorption of the lowest frequency. So lowest frequency, but now we want to absorb the lowest frequency. So it has to go up, but the smallest gap, because low frequency is low energy. So going up, but the smallest gap. So going up 1 to 3, 2 to 3, and then 3 to 4. The smallest gap would be 3 to 4 because 3 to 4 gaps are closer. So in this case here, that would be F. That's my answer. Okay, so these are the things that you want to keep in mind over here for the energy level or N level. Now, specifically, if you were talking about hydrogen, you see how hydrogen is like so many lines here. So the formula just for hydrogen itself, this is the Rydberg formula here. But don't worry too much about it. I will show you a calculation example. You might see this on your homework, but I try not to put this on your test because it's just a lot of busy work in math here. So electron, it's not election, it's electron. Energy of the electron is going to be final state, final line, whatever energy level, N level of the electron minus the initial, okay? And the photon that's being emitted is the opposite of the electron, okay? So energy of the photon that's released is basically the difference where the gap of the gaps are. So they come up with the formula here that tells you E of photon, and then they have this constant here, and really this is super simplified. There's actually a way more complicated equation. But the idea is you have the constant here, Rydberg constant here, and then 1 over the final energy line, N1, 2, 3, 4, 5, whatever the final state is, minus the initial state. And you can get the energy of the photon here, okay? And here's the question here. Which transition emits light with the shortest wavelength? The shortest wavelength would be the highest frequency. So highest frequency will be highest energy gap, and 3 to 2 would be the highest energy gap there, okay? So we were talking about the hydrogen line, right? So only certain energies is specific energy. So do you want to calculate what energy that is so you can provide that photon energy size? This is the equation here that it was given here. So I guess I'll go ahead and show you the exact formula. The exact formula is right here. So for a single electron transition, the energy of the photon is going to be negative is 2.18 earlier, so 2.178, 10 to the minus 18 joules, 1 over whatever the final level is, minus 1 over whatever the initial level, and the levels here, you got to square them, okay? So if you have to calculate, so let me show you that question here. We'll zoom in a little bit. If you see this in the homework. It says you describe the wavelength, determine the wavelength when you want to have emission from N6 to N5. So N6 to N5 are our levels. It's going to drop from 6 to 5, okay? So our formula is right here. So a formula is going to be final and initial, right? It's going to 6 to 5. So you literally put in the constant right there, and then level 6 is over here, level 5 is over here because it's final minus initial, according to that formula right there. So, and then you calculate it, you put it in, you get it in joules. That's the energy of the atom here. And remember, the atom here is going to be opposite sign for the photon. So if the atom is releasing it, the photon's energy is going to be a positive number. And once you get the photon's energy, if you needed to find, in this case, they asked for the wavelength. Well, once you get the energy, you plug it into this equation, and Planck's constant and speed of light there, you can get your wavelength calculated. So in this case, the wavelength is 7.46 10 to the minus 6 meters. And sometimes they will ask you to calculate in nanometers. But you can expect to see this on your homework, okay? So remember, all you do is you plug it into that equation there. So I'll show you the equation again. Is negative 2.178 10 to the minus 18 joules, 1 over n final squared minus 1 over n initial squared, okay? And that would be the energy change of the atom. And remember, the atom change is a negative number if it's emitting, and then the photon that's being emitted will be the positive energy. So it depends on what the question is asking. So you guys should be able to do that. Okay. So the next thing we want to talk about is, while we were talking about electrons here, we've been describing electrons as particles because we know electrons are things, we can count them, right? But electrons can also be viewed as a wave. That's why we're talking about duality, a dual particle wave, particle and wave duality in the nature right there. So we're talking about light can be seen as wave, light can be seen as particle. Now we want to look at electron. Electron was particle, and then now we want to look at the wave behavior of electrons. So combining these theories earlier, we were saying E equals mc squared, right? Because it has mass, and then energy is E equals to h Planck's constant, speed of light, or a wavelength. We combine these two together, you get that. Okay, and then we cancel out the c because c happens twice. So now h over lambda equals mc. C here is the speed of light, right? So let's say we rearrange it to be lambda here, h over m, and then whatever speed. And now if you put, this was earlier for the light. Now when we put it in an electron here, we can say if the electron is traveling the speed of v, we'll go ahead and speed of light changes the electron speed here. This is speed of electron here, okay? Now, h over m, mass of electron, and the speed of electron can give you the wavelength of the electron right there. So we're going to go ahead and try to calculate a problem where we'll solve for a wavelength of the electron. So let's go ahead and change the page right there, zoom out a little bit. Calculate wavelength of an electron. You're like, electrons have wavelengths? That's so weird. This is a weird chapter, right? Everything is like dual nature here. Electron traveling at a speed of 2.65 times 10 to the power 6 meters per second. Okay, so I want you guys to not get confused because this is called the de Broglie equation, okay? So h over m, and this is new again, but this here is not frequency like earlier. This is the speed, or actually the velocity of electron. And this here is the mass of electron, which will be given because I don't expect you to memorize that kind of stuff. I'll provide it for you, okay? And you'll be able to find this on your periodic table values as well. And of course, if you're doing this in your homework, pull up your slides, pull out your textbook, and you will see all these values in your book as well, okay? So Planck's constant, that will be provided as well. So let's go ahead and put this in. So lambda equals to Planck's constant 6.626 times 10 to the minus 34. Now joules, it was joule second, right? So I'm going to show you joules is actually kilograms and then m squared over s squared and then second right there. So this here is joules because it's millimeter. Anyway, so we have that over m, mass of electron, 9.11 times 10 to the minus 31 kilograms. That's how heavy an electron is. Really, really light. Okay, and then the speed of electron that was traveling, we put that in. So it was 2.65 times 10 to the power 6 meters per second. Okay, and then that way we can cross out a lot of our stuff here because our meters get canceled out over here, and then one of them anyway, and our seconds get canceled off over there, and then you have kilograms being canceled off over there. So all you have left is in units of meter. Okay, and units of meter here is 2.74 times 10 to the minus 10. So it's like kind of, you can report it in nanometer range too, but you can even go smaller. So this is a really, really small wavelength right there. So that's it for calculation for wavelength of electron right there. So I'm going to show you some proof here that they were talking about electrons as waves. It's really kind of crazy over here. Cool like observation here. So they noticed the electrons were doing diffraction patterns. Okay, they tried to do experiments over here. So when they had a source of electrons coming out, and then what they observed was if you put it through slits like that, you see interference pattern. The way it interfered like this here is only if there have wave particles, wave forms, have constructive interference and destructive interference, like waves. Now, if it wasn't a wave form, if you put them through light, you only see two lines, the electrons through two slits, I mean. You only see two lines and you don't observe this. So they say that's how we know electrons have interference patterns like waves do. And that's how we can calculate the wavelength of electrons. Okay, so now what's crazy is there's two properties, right? There's wave and there's particle nature. So when you try to observe the wave nature of the electron, you can't observe its particle nature. Like you can see one at a time. You can see it as a wave with the interference pattern, and you can also see it as a particle depending on what happens here. So wave and particle nature here are complementary properties, okay? But you only know one or the other here. So whenever they try to find, observe both of them happening at the same time, you can't find it. You can only observe one kind of property at a time, either a wave or either a particle. But they have observed it coming out as a wave, and they have observed it coming out as a particle. So basically, there's two natures of it, and then you can see that if you know one part, you won't know the other. So it says here, Heisenberg uncertainty principle says that you can't know both the position and the speed. So you can know either the position, the place it's at, or the speed of the thing. You won't be able to know both of them at the same time. Okay? So because we don't know both things at the same time, we will actually describe the probability of the electron being at a certain location. So when you have an electron, you either know where it's at or how fast it's going. But because we don't know both things at the same time, we calculate something called the probability of the electron's position. So when we calculate it, it actually comes out in an equation called Schrodinger's equation. I'll show you that. But so this is classical physics. When you throw the ball, you expect it to go in that right here. Now, if you have quantum mechanics here, electron in classical physics was just go in one orbit here. But if it was quantum mechanics, you're like, well, it could be here, 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 here. We don't really know. But here's the probability of where it's probably going to be at. Okay, so that's the difference here. This is quantum mechanics. This is classical physics. So Schrodinger's equation here tells us we're going to solve for the superposition of, well, basically the answer is you're going to look for where the electron is likely going to be. Okay, you guys heard of Schrodinger's cat? You should look it up. It's a really cool. Well, it's not a real experiment. It's just a imaginary cat that he talks about. Okay, so make sure to read about it, and there's actually probably a video of it in the beginning 3D text as well. Anyway, let's talk about Schrodinger's equation. Now, when you solve them, it comes out in quantum numbers, okay? But I want to show you the solutions first. So these are the solutions. Probability density of some orbital. Here's one of the solutions here. Here's the density. It turns out to look like a sphere. Okay, and the way we want to describe the sphere here, we use quantum numbers. We have sets of 3 kinds of quantum numbers. I'll talk about them. But this is one solution right here. And this is 1s orbital, okay? And then they have all kinds of solutions. They have 2s, 3s solutions. They have p orbital solutions. So the orbitals are the location, is the probability density map of where the electron is going to be. And that's when we draw them out like that, okay? So this is p orbital solution for the quantum mechanics, Schrodinger's equation, and then d orbitals look like this, and then you have f orbitals. So it's like complicated solutions. But we're gonna go ahead and simplify. You're not gonna be doing the math. When you have to calculate just for 1s, it took pages and pages of calculations actually, if you were to write it out anyway. And of course nowadays we have computers to do that for us too. But let's talk about the solutions that they have, the answers that they come up with, okay? So it's gonna be represented by quantum numbers. So quantum numbers have different levels here. So there's principal quantum number, n. There's angular momentum quantum number, L. So n here is the first number that you see. L is dependent on what n is. It's limited about what n can be. I'll show you guys in a little bit. And then you have magnetic quantum number that is ML, and it's dependent on what L is. So it's like this is dependent on this is dependent on that. So really the first number we want to talk about is principal quantum numbers. They're going to be in integers like 1, 0, 1, 2, 3, or whatever it is, okay, the values here. So n is the principal quantum number. It tells you about the energy level. It corresponds to Niels Bohr's energy level, or like the hydrogen, the Rydberg picture, the emission spectrum of the hydrogen. You see how the line's like level 1, 2, 3, 4, 5, right? So you start at the lowest level, and the lowest level you have is level 1. Because notice when I was drawing it, the level was level 1 at the lowest, and then you go up in higher energy level, N2, N3, N4, N5, and 6. It keeps going up, okay? So energies are described as being negative. It's because when the atoms is negative and the photons is the opposite of that. Anyway, that's that level right there we're talking about when we talk about Rydberg energy here. So I'm going to show you the picture of levels energy for n. So quantum number n tells you the energy level. N1 is the lowest energy, N2, N3, N4. These are the energy for each level here calculated. And then of course, if you do the electron from N3 to 2, you can see the difference between the energy levels there and get the energy of the photon that way, okay? But that's, or photon or electron, depending on what you're talking about. So that's energy level, N, okay? Now, N starts from 1 all the way 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 all the way to infinity. But the lowest one is N1. And then the next number is angular momentum quantum number called L. And L tells you the shape of the orbital. Like, is it a sphere? Like we saw some spheres, and then we saw some dumbbells, and then we saw some really complicated shapes, right? So that's what L tells us. And L is limited by N because it can only go from 0 all the way to N minus 1. So if my N was 1, L can only be 0. If my N is 2, L can be 0, L can be 1. So those are your options right there. And then if I say I have N level 3 here, if my N was level 3, what are my options for L? L could be 0, L could be 1, L could be 2. But L cannot be 3 because N was 3. So those are the limitations. It basically stops at N minus 1. So whenever the L options are, if L is 0, it's an S orbital, a sphere. If L is 1, it looks like P orbitals, which is 2 balloons, like a dumbbell shape. And then if L is 2, it's 4 balloons. It's like 2 dumbbells stuck together. And L is 3, it's 8 balloons, basically really complicated structure. I always tell my students, if you remember what S it looks like, it's a sphere, P is a dumbbell, D is 2 dumbbells, and if it's more complicated than that, then it's F orbital, because if you don't recognize it, it's F. Okay, so L is 0 means S orbital, L is 1 means P orbital, L is 2 means D orbital, L is 3 means F orbital. So you're like, okay, so what does that even tell me? So that's these 2 levels here. I want to go ahead and write them out for you, and then we'll loop in the third one, which is magnetic quantum number. So we have principal quantum number, and we have angular momentum quantum number. Agree? So I'm going to go ahead and write it out for you. So we want to start at quantum numbers. So quantum numbers are solutions to the Schrodinger's equation right there, where you're solving for like the duality of like particle and wave nature, and then you can end up with the probability of where the electrons are going to be. We don't know exactly where, but we can tell you a probability map of it. So these are the solutions here. They're represented with numbers. So the first one is principal quantum number, and it's N. Okay, and then I'll just do a short small little picture of it. It's like level 1, level 2, level 3, level 4. They get closer together. Okay, what does N tell us? N tells us energy levels. Higher N, higher energy level. And N starts from 1, goes up to 2, 3, 4, 5, blah, 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 all the way to infinity. Infinity and beyond. Okay, so that's the first one. And then we talked about quantum number. The second type is angular momentum. Quantum number. We call this L. So N is the first one, and then L is the second one, okay? Now L is related to N. It's stuck under the restrictions of what N is. So L tells us the shape of an electron orbital. Now remember, what in the world is an orbital? Orbital is a density map. So, that's where the orbitals represent. That in that map, in that orbital, that's where the electron is most likely to be at. We don't know where in the orbital, but it's somewhere in there. And sometimes it's on one end of the orbital, sometimes on the other end. We don't know, but that's the probability of it, okay? So L tells us the shape. N tells us what energy level. Is it low energy? Is it high energy? L tells us what shape it will be. So on the slide there, we were talking L0 is S orbital. And then it looks like a sphere. Yeah, but my sphere doesn't look that good, does it? But you get it, it's a sphere. L is 1. And then L is 1. It'll look like a P orbital, where it looks like a dumbbell. And then L is 2 is a D orbital. It looks like 2 dumbbells stuck together. And actually there's one of them that looks like a donut ring around the dumbbell. It's like you go work out, carry some dumbbells, and after that you can eat a donut. That's how I remember it. Okay? So you have 2 dumbbells, that's D orbital. And then L is 3. Those are the ones that we know of on our periodic table. There's more, but that's all we need to know right now because our periodic table shows you only up to F. So it's kind of cool. I'll show you that how all this number are related is shown in a periodic table. It's really, really cool. So F orbital, and it's like complicated structure. So I said, if you don't recognize from the list before this, it must be an F orbital. This is like process of elimination. If it doesn't look like a sphere, doesn't look like a dumbbell, doesn't look like 2 dumbbells or a dumbbell with donut ring, then it's an F orbital, okay? And then what was the rule for L? L is limited by, you can go up to 0 all the way up to n minus 1, okay? So if I have n equals to 1, my L can only be 0. My L cannot be 1 because n minus 1 is 0. 1 minus 1 is 0, okay? So that's that. And if I have n equals to 2, my L can be 0, agree? If n equals to 2, I have another option, L can be 1, correct? But can n2 have L2? Nope, impossible because it's stuck to n minus 1. So then you go another level, you go n is level 3, and my L can be 0. If my n is level 3, my L can also potentially be 1. My n is level 3, my L can be also 2. So these are like basically your potential places of where the electrons are going to be. So it's saying here, on level 1, you can only find it in a sphere. On level 2, you can find it in a sphere and a dumbbell. Level 3, you can find it in a sphere, dumbbell, and 2 dumbbells stuck together. That's the pattern there, okay? So this here tells you 1, 0 is S orbital, so 1s orbital. So this is 2, 0, 2, 0, 2s, 2s orbital. And then you have 2p orbital. And then you have 3s orbital. And then you have 3p orbital, 3d orbital. So basically that tells you what the potential orbitals are. And we keep going, we can go to level 4. Like level 4, you'll have 4, I'll write it out since we have space. N4, L can be 0, N4, L can be 1, N4, L can be 2, N4, L can be 3, right? So this will be 4s orbital, 4p orbital, 4d orbital, and 4f orbital. Ta-da! So you can start seeing the options, and that's why you have never heard of 1p orbital, because it doesn't exist. Quantum number rule says it's impossible. 1p cannot exist. You have 1s, 2s, and 2p. You can't have 1p, right? And then they say you have 3s, 3p, and 3d, but you've never seen 3f because it doesn't exist. Because of the rule says L can be only up to n minus 1. So that's the idea there, okay? So let's go to the next number, okay? The next number is called magnetic quantum number. So I want to show you the slides on it, and we'll write about it in a little bit. So magnetic quantum number tells us the orientation or direction of where the orbital is pointed, Okay, so what is the ML going to be? It's limited from negative L all the way up to 0, all the way up to positive L, including 0. So if L is 2, my options are negative 2, negative 1, 0, plus 1, plus 2. There's 5 different directions it's pointing at. So I want to go ahead and explain this in the pictures from these guys here. So I'm going to go ahead and do this on the next page now, okay? So first number is principal quantum number N. Second number is L, angular momentum quantum number. The third one is magnetic quantum number. Magnetic quantum number. And after this, I will show you on your periodic table where all these guys are, and then that is actually the end of chapter 8. And the next part that's related to this is somehow stuck in chapter 9. So I'll kind of give you a little preview maybe and show you what's coming up in chapter 9, but we'll go over that in detail, I guess. Chapter 9 has to do with the fourth quantum number. So there's 3 of them. The fourth one is in chapter 9. I love how they separate it like that. Okay, what does ML tells us? ML tells us the orientation or the direction of the orbitals. Okay, so ML is related to L, is all the way from negative L, going up to 0, going up to positive L. Okay, so these are whole integers. So if I have N is 1, my L was 0. Agree? We said that. When N is 1, oh, not N is 1, N is 2, my L was 0, and N is 2, L was 1. Remember that? We said that. Okay, now we stop there, and then I'll do N3 in a little bit. So when N is 1, L can only be 0. If L is 0, what's my ML option? 0. Okay, so that means there's only one orientation of 1s orbital. Well, it makes sense. If it's a sphere, you can't really point in any other direction. It's the same every other way you turn it around. So that's why when you have L0, ML is only 0. So the fact that it's 0, it tells you that the orientation is at position 0. Okay, so it's right there. And then N is 2, L is 0. And then because L is 0 there, ML is also 0. So that means if you had a 2s orbital, 2s is bigger because of the higher energy level. It's literally one option of where the orientation will be. ML code 0. Okay? And then if L is 1, my ML now I have options. I have negative 1, and I have 0, and I have plus 1. Okay, so I have 3 different orientations here. So I can actually rewrite it and say this is L2, L1, ML0, N2, L1, ML plus 1. Okay, so that's like a series here. This one describes one electron, this one describes another electron, this one, I mean not electron, orbital. That one describes another orbital. So you have here 3 orientations of 2p. So we have, it was px, py, and pz, but we don't need to worry too much about it. So this is 2p, 2p, and 2p, okay? So your job is to know there's 3 different kinds, and it's really 2px, 2py, 2pz, because we have, if you have a axis here, this is x, remember, and that's y, and then z is in 3D, I guess, how would you draw z? Z is like coming out towards here. You see, I didn't do a good job. I know, I should do this exactly. If you do it flat on a paper, the y goes that way. So that's on the paper, okay? That's flat, and then z is sticking out. Then I can draw it like that. Okay, anyway, x, y, and z. So if you have 2px, it's literally on the x-axis, so it goes like this. And then 2py is on the y, and then 2pz on whatever axis is going to be. Okay, so that's what it looks like. I guess I need to fix my Y. My Y should be bent a little bit more. It's like that. So different orientations, okay? And then let's go to level 3 just for fun, okay? So you can keep going, and then I'm not going to draw F because it gets too complicated for me to draw. My art skills don't go up that high. So N is 3, L is 0, okay? And then ML will be 0. So there's only one orientation of 3s. So 3s is going to be bigger than 2s. Did I draw bigger? Yeah, I did. Okay, good. Woohoo! And then we got N is 2 and N is 3. L is 1, right? And then under L is 1, I have ML is -1. And then ML is 0. ML is +1. So this is N3, L1, N3, L1, right? So this is 3s. I mean, not 3s. That's 3s right there. So this is 3p x, 3p y, 3p z. Okay, so the 3 kinds. So the difference between this guy and that guy is this one's bigger. So I'm going to draw it a little bigger if I can. I hope that's bigger. And then the y is bigger. And then the z is bigger. Okay? And then let's go to the next level. So N is 3. Oh, I'm going to run the space. Let me do down here, okay? So N is 3. L is 2. Option, that's another one option, right? If L is 2, ML option is -2. ML can also be -1. ML can also be 0. ML can be +1. ML can be +2. Remember, because we said it goes from -L up to 0 up to +L. So -2, 1, 0, +1, +2. Okay? So this is all under N3, L2. So for that one there, if we were talking about d orbitals, because L2 is d orbital, so this is 3D, 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 3D. Okay, so I'm going to go ahead and give you the names. You don't have to memorize this, but it's kind of cool to see them. So there's D, X, and Y, D, Y, and Z, and then you have D, X, and Z, and then you have dx squared, y squared, and then you have dz squared. Okay, so dz squared is the donut that looks like a donut ring with a dumbbell. So I guess if I try to draw it, it will look really ugly. So I'm just going to show you the picture of it, okay? But this one here, the z squared, is this guy. I can draw that. Okay, and then we have the other 4 on different orientations. And then right here, here's the picture. So slide number 52, you can see all your options right there. So this is X and Y, so it's on the X and Y plane. And then Y and Z is on the Y and Z plane. And then X and Z, X squared, Y squared is on that X and Y only. And this is Z squared. Okay, so that's your orbitals here. And that's how you would say there's 5 different orientations of this orbital here. So 3D, there's 5 options. Okay, now when you start looking at the energy levels here, I guess I'll draw it on the slide here since we only have level 1, 2, and 3. So I'll try to show you how it looks like. So we have level 1, and then we have level 2, and then we have level 3, right? So level 1, N is 1, N is 2, N is 3. And then under 1, we have 1s, and then 2, we have 2s. And then under 2s, we also have 2p. There's 3 kinds. P is a little higher energy than s. So the 2p is going to end up over here. So there's 1s, that's 2s, that's 2p. And then there's 3s. And then there's 3p, And then there's also 3D. 3D is higher than 3P, so it's like right there. That's the energy levels right there. And I'm going to show you a picture of it in the next chapter. But this is 1S right here, 2S, 2P, and then 3S, 3P, and then 3D. So those are the energy levels right there that we're drawing, okay? And let's go over this. I'm going to show you. When you get higher and higher energy levels, you actually get something called, they call level 2 and level 3, although it's a sphere, it's not the entire sphere that has the electrons. There's actually spots where it's not possible to have electrons. Those are called nodes. You don't need to worry about it, but it's just kind of cool that it's not in the whole entire sphere. It's like portions of the sphere. And the probability goes to 0 at those points, and that's why we call them the nodes. And then we have p orbitals. P orbitals have, they exist on the two sides, but not in the middle. So it's kind of cool the way they have it. But they will have the node at the nucleus for p right there. And then for d orbitals, there's also nodes like basically in the middle right there. It's not possible to exist right there. And then the higher levels, there's also going to be nodes like inside the orbitals. The D, like not all of it will be filled. There could be nodes on the inside as well. Okay, so each orbital is now described like this. So we have N, L, and ML describes one orbital. It tells you the energy, and then tells you the shape and the orientation. So that's what I was trying to draw. It tells you how good my art is, right? But you guys can get my point here. So that's level 1, level 2, level 3. We just worked it out, and that's why we don't see 1P existing. We don't see 2D existing. It's because the rules of the quantum numbers that solve from the Schrodinger's equation. Okay, so we have that. And then the question here, we got some questions. When you go over these questions, it says here, what are the quantum numbers, for example, for 2s, 2p, or orbitals in n principle level 4? How many n4 orbitals exist? So basically, you saw how we were doing n3, like on this page here, all n3, n1, n2, n3. That's a lot, right? They want an n4. You're like, whoa, there's a lot of them. So what are the quantum names and numbers for N4? So on N4, you have N4L0, 1, 2, 3, and then you have all these potentials here. So you have level 4, you have 4s, one orbital here. Level 4p here, you have three of them. And then you have 4d, you have 5 orbitals, and you have 4f, you have 7 orbitals. So that's all on level 4 alone. So level 4, n is 4, L can be 0, L can be 1, L can be 2, L can be 3. And under these L's here, there's all these different orientations. So each one of them are orbitals. So basically 1 orbital, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 orbitals altogether. And that's how you can tell. And then obviously this one here, like if you have N4L0 and ML0, that's an s orbital. N4L1 and ML-1, that's 4px, 4py, and 4pz. Like, so that's under L1 category. And L2 is 4D, so this is the first 4D, second 4D, third 4D, fourth 4D, and fifth 4D. And then you have 4f orbitals here. So those are the names of it, okay? So that's naming the orbitals. We kind of wrote it out here for the level 3 already. So let's go over quantum numbers here. It says the sets of quantum numbers is supposed to specify an orbital. One set, however, is wrong. Which one? So let's look and see which one is wrong. So N is 3, L is 0. Is that possible? Yes, that's possible. ML is 0, that's possible. In fact, which orbital is this pointing to? This is a 3s orbital. Okay, N2, L1, ML-1. Is this possible? Yes, because N2 is level 2, L1 is P, so this is 2P. And in fact, this is a third 2P because it's plus 1 minus, it's minus 1, 0 plus 1. So this is the first orbital. So it's 2px. And then let's look at this one. N1, L0, ML0. Is this possible? Yes, this is a 1s orbital. Okay, let's take a look at this. Level 4, L1, that's still good. If L1, can ML be -2? Impossible, because the limits when L is 1, ML can be -1, 0, or +1. It cannot be -2. This one here is wrong, okay? Now, let's take a look at this next question here. It says, which one here is wrong? Replace it with something that's allowed. So N3, L3, that's not right. L can only go up to N-1. So the maximum it can go to is 2 over here. So I'll put N3, L2, and ML plus 2. That would make sense. So if it's N3, L2, it will be a 3D orbital, okay? 3F doesn't exist. N2, L1, ML -2. N2 is level 2, L1 is P. If L1 is P, can you have -2 orientation? No, you can't, because it's -1, 0, and +1. So I would change this to a -1, I guess, or 0 or +1, okay? And this N1, L1, ML0. If N is 1, L cannot be 1. L can only be 0. That will give you a 1s orbital right there, okay? So that's how we would look at quantum numbers. So 3 numbers, N, L, and ML, gives you the orbitals description of one orbital. 3 numbers describe one orbital, okay? So that is basically what we're going to cover here. And in the next chapter here, I want to show you that each orbital can hold 2 electrons. And that's when we come up with our 4th quantum number, where we have quantum number for each of the electrons, spin up or spin down. Okay, so this is the end of chapter 8. Look forward to chapter 9.